All right, happy Thursday, everybody. Thanks for braving the balmy weather to show up in person and or braving whatever you're braving to be in your living rooms or wherever you're coming to us from the Zoom room. So we have the remainder of lecture 1 to get through. We may get through all of it, maybe not, and get started on example 1. What you have to be working on then based on what we're covering this week is your first formative assessment. You should be able to answer all of the questions by the end of today. You can do half of them now. And that is due Monday night. Just as a reminder, you get 2 points for giving it an honest try. I don't care if you're right or not. The purpose is to provide an opportunity for us to go over things as a structured review on the next class, and for you to be able to ask me questions. Like if there's things that's like, yeah, I'd like you to go back over that, or this reminds me of this other thing, and can you talk about that? All of those sorts of dialogue opportunities is what that's intended for. Last time, what do you remember about last time? Let me give you a nice, prettier picture to look at here. I'll take words, gestures, symbols, anything you remember from last time. What were we talking about? Effect size and power. Yeah, what's an effect size? How would you describe effect size? Yes, sir. How big it is? And how do I know what's big and what's little?
That basically like 0 is no correlation, 1 and -1 is a strong correlation.
Yeah, so the thing about effect size is that it's in some kind of common metric where we've taken away all of the units and we're working with the idea of a standardized quantity. So effect sizes often use an R, or what's known as an eta metric, for instance, where the strongest you can have is 1, which would be a positive association. The strongest negative association you can have is -1, and 0 would be none. What's another letter that goes with effect size you may have heard of, besides R? Yeah. D, yeah, there's the D family, because there's like G and delta and a couple other ones that go into there. Those are for mean differences. So that's a group mean difference in standardized units. And the Zoomers say yes, it helps us, effect sizes help us to compare the strength of predictors. They also help us to convey in an absolute sense how much something matters. So significance is a function of sample size and effect size. That means if you have a significant relationship, it could be because you got a lot of people, because you got a strong relationship, or some factor of both. So yes, we did talk about that. What's a general linear model? What does it mean if I say I used a general linear model? What kind of outcome am I trying to predict? Yeah, something that's continuous, something that's definitely a number. Yeah, we use a linear model to predict it. So we pretend that the slopes can generate predictions without boundaries, because it's continuous outcome. What do we assume about the e's, the residuals of our prediction? They're normal, right? Does that mean that y has to be normal? Does not. That's a common misconception. The original outcome does not have a distributional assumption. It's the e's that are left that do, meaning the part that's left after prediction. E's are also supposed to be 2 other things in a general linear model besides normal. One starts with an I. I-N. I-N-D. We'll play hangman. Independent. Yes. That means that there's no reason why the E of one person would have any more relationship to the E of somebody else. That will be violated if people come in naturally occurring groups, like families or classrooms, or people see the same therapist, or any of those kinds of things. So if we need that, we need a different kind of model. That's a different class, or at least towards the end of this class, heading into different classes. There's one more. E's are supposed to be normally distributed and independent, and along with normally distributed comes one other component. This one starts with an H, and it's a long word. Has like 17 syllables in it. Yeah, homoscedastic. Yeah, hetero is the bad kind. Yeah, said more simply as constant variance. Another way of thinking about that is that the model works equally well for everybody. The spread of how far off you are should be the same as you move up and down y as you move up and down x. That goes with the idea of using a normal distribution. So normal means that you have a separately estimated variance, and that variance holds for everybody. So that's what makes a general linear model, are those three things, regardless of what kind of predictors you have. So if I have categorical predictors, then that's called ANOVA. If I have continuous quantitative variables, that's called regression. If I have a mixture of both, it might be called ANCOVA or regression. But those words don't really mean anything in terms of what the underlying model is trying to do. Let's see. Power, that was another thing we talked about briefly. Power is your chance of finding an effect that's actually there. So that's one of the reasons why we would report effect size, is to help other people plan their power to do research. Also to get a sense of like how lucky you are, right? There's a huge replicability crisis. And when you see something like, I have a 3-way significant interaction for a sample of 15, it's like, I think you just got lucky. So reporting power is one way to indicate what are the chances of this replicating across future samples. If you have a very low chance, you might have less confidence in that result, even if it is significant, because you got lucky finding it. Let's see. Now I can move the picture here, go back to the slides. We talked about how to put predictor variables into a model. Basically, there's two distinctions of kinds of predictors, and it's categorical versus quantitative. So if you have a number, a variable that is an amount, you can put it in the model directly as a predictor, so long as you have centered it. That was a vocabulary word. What's centering mean? Make 0 mean something. So you would either add or subtract a constant so that 0 means something. Yep. And why does that matter? Hiding this again. If I have a more complicated model and I don't center, what was the end of that? I'm sorry, I can't hear you. It will break down? It won't break down, but you can end up with information that is not useful, is what I would say. So at a minimum, because the intercept is always the expected outcome when your predictors are 0, we need the predictors to have a meaningful 0. But in models with interactions, the so-called main effects are also conditional on the interacting predictors being 0. And so in order for them to mean something to us, we want to have centered variables. So that's where we're headed towards the end of today. If we have a categorical predictor, such as like, what's your favorite pet? Where number 1 is cat, obviously. Number 2 is dog. Number 3 is fish. Can I put that in the model as is? No. Will the software let you? Yes, it will. It will happily compute a slope to describe the effect on your outcome of cat versus dog versus fish versus whatever. Does that slope mean anything, though? No, it does not. So what do I need to do if I have a variable that represents kinds instead of an amount? Code it, which means what in practice? Say it louder. Yeah, the easiest way to do it is to pick one of the groups as the reference, and then I create separate new variables that describe then each other group relative to that reference in some capacity. So that's one coding scheme. Dummy coding is what I'm talking about here. More specifically, indicator coding. We talked about that last time. So if I have 3 groups, I need 2 new predictors. If I have 3 groups, I need 2. If I have 4 groups, I need 3. If I have 5 groups, how many do I need? 4, yes. Because if I have an intercept, that's why it's always -1, then I have all of the information I need to give each group its own mean and to figure out if the means are significantly different from each other. So how you rearrange the zeros and ones is up to you. It's what do you want to know. So if you have a nominal variable, like cat versus dog versus bird or whatever, then if there's no inherent ordering, you can pick one group as your reference and create new predictors that differentiate each other group. So the name of this column is A versus B because when they're both in the model, that's what it's going to indicate, how the B group differs from the A group. The last column then is going to indicate how the C group differs from the A group. What if I want to know B versus C? Yeah, do you remember in the back? Yep, take the difference. So in this example, where we had 4 groups, if I have my coding scheme such that this variable D1 is how the first group differs from control, D2 is how the second group differs from control, and so on, then the differences among the 3 that are not the reference are differences in the corresponding slopes. So I will show you today how to get that out of software if you haven't learned that already. Alternatively, if you denote your variable in the program as a factor variable, for instance, or an I-dot variable in Stata, or a class variable or a discrete variable, then it does this coding system for you. The only catch is that you have to understand what the program is doing in order to interpret the results. And it's not always obvious, but they're going to, if you have an intercept, it's going to remove one of the columns so that you still have one reference group and then differences relative to that. All right, and then we talked about semi-continuous predictors and other kinds of coding schemes to get both kinds and amounts. So you're limited only by your own creativity and how you set these things up. Okay, I think that was about where we left off was with this one. Any questions or other comments that you want to ask before we jump back in? No? Feeling okay so far? So far, so good. I'm guessing it's like, well, yeah, this makes sense, but I don't know if I'm following until I have to do it. That's always the case. Your first homework is going to give you a chance to practice all of this. All right, so let me make this big here. So then the idea of how we represent associations in a model as a function of multiple slopes. So the term general linear model. The general part actually has a very, very specific meaning. It means that you have an E residual that's normal with constant variance and that's independent. The term general came from the idea of the unification of regression and ANOVA, which were initially thought of and taught as 2 separate things. And the general linear model was like Jacob Cohen in 1950 or so that put that terminology together. And at the time, it was the most general thing. And then other people came along and were like, no, actually, that's just a special case of my more general thing, which is generalized models. So that's the general versus generalized part. The ized means you're predicting some other kind of outcome that's not necessarily continuous. The linear part. This means that the equation follows a format where it's slope times variable plus slope times variable. So you can have nonlinearity in 2 different kinds, in the variables or in the parameters. Have you heard these terms before? Is this new? Maybe? So linear means slope times variable plus slope times variable. Nonlinear in the variables would be something like adding in x squared as a predictor to create a curved line instead of a straight line. It's still slope times x plus slope times x squared, though. It still follows that same form, so it's still considered a linear model, even though it creates a nonlinear shape of the prediction. Alternatively, a truly nonlinear model would look something like this, for instance, where this is slope times e to the slope times other variable, like something that has a nonlinear function in it. So these types of models are much less common. They're much harder to estimate. So this is what linear means too. It doesn't mean that everything that we create is necessarily a line. It just means this is the form that it follows. So then the question is, how many distinct slopes does it take to fully explain or fully represent the relationship between a predictor and an outcome. If you're talking about a two-category predictor, so a binary X, you only need one slope, because it's how the one group differs from the zero group, the int. That's all you need. Likewise, if you hypothesize a linear slope for a quantitative variable, then you only need that one slope to characterize that linear relationship. Other ways that you can trick this same thing. So if you're interested in a slope that shuts off, like something that kind of looks like this, like where more stops mattering, you can trick a linear model into giving that to you if you log transform your predictor and then fit a linear slope for that log transform predictor. The end result is a line that looks like this instead. Similarly, you can do what's known as a logit transform, and you can use one slope that creates a logistic slope, which is a slope that goes down, comes up, and then shuts off again. So there are ways to take a linear model and coax it into giving you nonlinear relationships. Other kinds of nonlinear relationships require more than one slope. So if I have a quantitative predictor and I think that a little is good, a lot is bad, or excuse me, middle is good and a lot is bad, like something like this. Like there's a famous relationship between like performance and arousal. So if you think about like performance as something where higher is better, like if you don't give a shit, that's bad, right? If you're all worked up and you're too nervous, that's also bad. But somewhere in the middle, right, where you're harnessing your energy in a positive way, like you're excited, but you're not like over the top, like that's a quadratic function. In order to build a function like that, you would have to have your predictor in its original form and then predictor squared, and that would create that U-shaped relationship. So then it would take two slopes working together to fully characterize how that X relates to that outcome. The same is true for categorical predictors where there's more than two groups. So if I have three groups, I need two slopes to fully differentiate the three groups. And in each of these cases, where more than one slope is needed to describe an association between one variable conceptually and one outcome, I need to find a way to lump the slopes together and get a joint hypothesis test. So like if I'm talking about does, favorite kind of pet predict my outcome, I need the two slopes that differentiate my three kinds of pets together as a hypothesis test. If I want to know how arousal relates to performance, and arousal is a quadratic function, then I need both the linear and quadratic slopes working together to talk about that relationship. So when you're trying to test multiple slopes together at the same time, we need to be able to ask for that additional kind of comparison. So this is what's known as a multivariate Wald test in the literature. You may have seen this before, but I can guarantee you've seen a couple special cases. The F-test for the model, does that ring a bell? Like, is my model significant? Is my R-square significantly greater than 0? That piece of information that shows up on your output, that's what I'm talking about. In that case, the F for the model is a joint hypothesis test of all the model slopes at the same time, and F is the average contribution of those slopes. So it's how much information was captured by your model divided by how many slopes it took to get that information, divided by how much information is left over, divided by how many slopes you could have added. So these terms are known as numerator degrees of freedom and denominator degrees of freedom, respectively. It works out to be then basically how much information did you capture per slope relative to how much information is left over per slope you could have added. Where like the worst that you would be is 1, meaning I didn't get any more than I would expect from chance. So you end up with this F that describes then how well the slopes work together. It's another way of thinking about it is as the significance test that goes with the variance explained for the model. Another instance in which you would have seen this is a so-called omnibus effect of omnibus main effect of a grouping variable. This is a Nova language. So like if I have 4 groups and I'm interested in their group differences, I would look at the omnibus main effect of group. If I have 4 groups, that's a 3-slope joint test. And that tells me whether there's a mean difference somewhere, and then I got to go figure out which one it is. Another instance of this, hierarchical regression. Have you heard those words before? Maybe. Okay, so that is when, like, I have a model, and then I add another layer of predictors to my model, and I want a significance test for whether that new layer means something. The significance of the change in R-square, that's another kind of F-test for this. So it's useful to know how to ask for these joint hypothesis tests, because there's going to be many times in which they're not given by default, or you're interested in a combination that isn't necessarily anticipated by the software. For instance, if I wanted to do something like, how much of my outcome is explained by demographic variables and how much of my outcome is explained by personality, where I might have a lump of demographics that's like age and gender and education level and stuff like that, and then I might have scores on like a personality measure with 5 dimensions. If I want to know like how much is personality, like as a concept, and I want to lump those 5 slopes together, I can do that if I know how to ask for that kind of joint hypothesis test. Same thing with the demographic info. So I want to make sure that you know how to do that moving forward, because you'll have to know how to do that in many cases. In generalized models, this stuff isn't spit out for you readily. By the way, it's F if we're using denominator degrees of freedom. It's chi-square if we're not. The difference between the two is that F is per slope and chi-square is not. So if you take F times the number of slopes, then you get your chi-square. So you can always get from one to the other. If you're testing only one slope, then the t that you get for that slope squared is the same thing as an f. Likewise, if you're not using denominator degrees of freedom, if you consider that estimate over standard error, instead of it being a t, it's a z, z squared is chi-square. So all these things sort of relate to each other in a very predictable pattern. The logic is that when you have smaller samples, these reference distributions are not going to be exactly correct in telling you where 5% starts. Basically, where the point is where you're far enough away from the null hypothesis that you're like, yeah, this is sufficiently unlikely. I'm going to say it's not likely. This is the right distribution. It's significant. The fewer the people there are, the further out you have to go to hit that point. And so the most conservative thing to do is to always use denominator degrees of freedom. At some point, it stops making a difference. But generalized software often does not use them. So you will get z's and chi-squares where you're used to seeing t's and f's, and I want to prepare you for that switch in terminology. The difference is just the reference distribution that gives you your p-value for how unlikely that result is given the null hypothesis. Okay. Other questions? All right, let's see an example, shall we? And you can say to yourself, yeah, I know how to do this, or, oh, I haven't seen this part before. One of the two. So I'm switching then out of the lecture slides to example 1. And on the course website, let me pull this up again real quick. Make sure that everybody has found all the stuff. So I have example 1 in a PDF document right here that has all the syntax, all of the output that we care about, and a bunch of annotations and notes about what means what. The original files that I pulled all of this stuff from are right here in a zip folder. So when you do your homework, do not start from the PDF, because if you copy over stuff from the PDF, it sometimes introduces weird characters into your syntax, and then it won't run for no apparent reason. Instead, if you go into that zip folder, let me show you here. Here's the contents of it. Move over here, please. Thank you. You'll see that I have plots. I have the data in Excel. I have tables and figures that go with the example. So this is from my textbook. There's various calculations in here, so examples on how to do stuff. And then I have syntax and output in R and Stata is what I'm covering, but I also have it in SAS because I already have it from SAS from when I did this before. Notably, all of these files right here are text files. So that means you don't need to be inside Stata or inside R to look at them and annotate them. You can open up any of these files inside like Notepad, WordPad, TextPad, whatever text editor you use. And so you can see exactly what all of the original output would have looked like. And then the parts that are important, we focus on in the handout. So all of these original source materials is where I would start from when you're looking for how do I do this in homework. You would take my models, figure out what needs to be changed to do your analyses, and then go from there. Does that make sense? Okay. I used to be in stats classes where we would sit in front of our computers and run things together. And that usually went off the rails real quick, because if you get behind, you can't like figure out how everybody got to where they are. And if you're busy trying to type and follow along, particularly if you don't have good eyesight, which is the case in me, it doesn't work very well. So rather than trying to do like live demonstrations where we're running things, this is the pattern that I've settled on. Let's just put all the important stuff in here so that you can focus on making sure you can follow the logic of what the code's doing and how to interpret the results. Whether you can push the button to recreate this, I trust you to be able to do that on your own and to troubleshoot that if you need to. So the way that I have this working then is I have Stata code and I have R code, and then I have a mixture of output for both to start with, because I know that there's folks who are interested in focusing on one versus the other. I have both for the first two models, and then I have, I think, primarily R for the third one. But if you're interested in only looking at one set of output versus the other, you can go to the original files for that. So this example is from chapter 2 of my textbook. The textbook that I wrote, by the way, is about longitudinal analysis. Chapter 2 of that book is about regression models with interaction terms. Now you might say to yourself, whoa, why did you put that in a textbook on longitudinal models? And the short answer is, I figured out after teaching this stuff for a long time that people's understanding of how to interpret an interaction term is very much hit or miss. And I needed people to be able to do that in order to do longitudinal analysis. So this was a necessary step on the way to something else, but the same is true. I want you to be able to interpret any kind of slope in a linear model in a familiar setting of regression first, before we make the jump into using these same kinds of linear models to predict other kinds of outcomes. So this is just making sure that we're all on the same page with respect to linear model principles in predicting a standard outcome without any additional layers of complication. Does that sound fair? Okay. So this is a fake data set, because fake people are very well behaved when it comes to model assumptions, but it's based on a real story. So back before I started specializing basically exclusively in quantitative methods, I dabbled in the world of cognitive aging. And a lot of the data sets that I worked on at the time were filled with older adults, and so this is from that part of my life. So we're looking at cognition as an outcome. It's a measure of crystallized intelligence, known as the information test within this sample. We're looking at age as a predictor, which is going to be centered at 85 years, because the age range in this sample is very old people. Grip strength is another predictor of cognition, which sounds kind of crazy. The measure of grip strength in the study that these data are based on was how many pounds per square inch you could squeeze with this little squeezy thing. That is commonly used in aging studies as a proxy for physical function or physical health. So whether that makes sense or not, I don't want to weigh in on that, but that's my predictor. It's centered at 9 pounds per square inch because that is about the mean for this sample. So notice for both of these variables, I'm picking constants that are towards the middle of the distribution, but they're not the exact mean. So when I get to the point where I have age and grip strength both as predictors, then I would say my reference person for my intercept is an 85-year-old person who can squeeze 9 pounds. I can readily picture that kind of person in my data set. I also have a binary indicator of sex, which is going to be coded with men as the reference, so they're the 0 and women are the 1. And then I have a 3-category variable with respect to dementia status. In the original study, there were people who never got dementia during the course of the study, people who were diagnosed at some point while the study was happening, and then there were people who entered the study already having a diagnosis. So those are the three categories that I have. This is an ordinal variable, but I'm going to be treating it as nominal in terms of the coding, using none as the reference, and then slopes to differentiate future versus none and current versus none. I've got a sample of 550 adults. So we're going to look at three different models. One is just what I call a main effects model, meaning there are no interaction terms. We'll start with that one, and then we'll talk about what to do with interaction terms in the last two models. Okay, so any questions on the setup thus far? All right. So in terms of the coding schemes here, these are commands that are designed to import data. This is stata code. Create the new predictor variables, either center them or recode them, and add labels. So I'm importing a stata data set from this place. This is another way to define a working directory, by the way. What it's doing is defining an abbreviation called filesave that's going to hold this path. And that way, anywhere in this code that you see that word filesave, it's going to refer to that place. That way, if I move where my files are, I only have to change it once, and it changes throughout the rest of the package. So I'm importing the data set. I'm creating new variables here. So in stata language to first, and then I'll show you what this looks like in R. The gen command stands for generate. That's how you make new variables that are just simple functions. My naming convention when I make new predictors is to add the name of the centering constant to the end of the name. That way I know that age has been centered at 85 when I'm looking at my output, and I don't have to try and remember what the centering point was. So age 85 and grip 9 are my two new variables created out of the original variables age and the original variables grip. When you make new variables, they need to be a different name. Otherwise, you're going to write over the same column, and that is bad. So I don't care what you call this as long as it's not age, because the name age is already taken. Same thing with grip. So it's new variable equals old variable minus constant. Next step is to carve up dementia group into a series of dummy codes. And the way that I name these is with abbreviations for who is the reference and who is the alternative. So my choices are none, future, and current. So DEM for dementia, NF is going to be none versus future. DEM NC is none versus current. Then the remainder of this is systematically replacing values based on meeting a condition of which group they're in. So the first lines here say stick zeros in those two new variables if we're talking about dementia group 1. The next two lines here, by the way, the green is comments. That's why I'm skipping over those. So these are notes that describe what the code below is actually doing. These two lines are going to stick in a 1 and a 0 if we're talking about group 2, and then stick in a 0 and a 1 if we're talking about group 3. And no, these two equal signs is not a typo. R does this too. 2 equals is an equality condition, like if it's a 0. So 1 equal means make it a 0. 2 equals means if it's a 1. Then last but not least, I'm labeling all of my variables so that I know what's what. And then when I look back at my work 3 years from now, I'll remember what I did and why. This command right here subsets my data to only the rows that are complete with respect to all of the variables that are eventually going into my model. If you don't do that, it will be done for you, but inconsistently. So if your goal is to have the exact same sample for every analysis, you would need to set it up that way ahead of time if you have missing data. And you might be thinking to yourself, wait, isn't dropping cases bad? Yes, yes it is. But the way around it is not this class. That's another class. You would need to find a way to bring those cases, that information into the likelihood function to be estimated with the rest of the model is the short answer. Okay. Any questions on stata code thus far? Looking at the chat too for you Zoomers. No. Okay, R code. So here is my, my caveat with respect to my R code, okay? I am not a member of the tidyverse. I am a member of base R. So all of the code that I use is trying to make the most of base R functions whenever possible, because they are the most transparent and I believe the most understandable, rather than having functions of nested functions of functions. So if you learned how to do this stuff a different way using the tidyverse, and that way works for you, great, do it that way. There's always more than one thing to accomplish the same goal in a software package. But this will work, and if you're new to R, then you can follow my example and with a few select find and replaces, make it work for whatever you're trying to do. So this may be a different way of reading in data and making new variables than what you've seen before, but it is another way. So I'm used an Excel version of the data set here. I am first defining a program level variable called file save that holds the path to where this is. And note the weird pattern of slashes here. This is sort of inconsistent. I'm defining another one that is the name of the data set to be imported. That way, if I change where stuff is or what data I want, I only have to change it here, and it changes everywhere else throughout the program. Defining a working directory as this same place right here. I am importing the Excel data set, and I am calling it example1. I'm using a function, one of the few exceptions to the base R, called read Excel. And that is then pasting together the path to the file and the file name to create one long string. Because sometimes these import packages render tables or tibbles, whatever the hell that is, or data something else and it needs to be a data frame, I always have this next, just in case it's not a data frame. Then it becomes a data frame because most of the calls to analysis packages use data frames. And then I'm also sorting the data by ID. Then comes the new predictors. So it looks similar in structure to what is in other languages, with the exception that the name of the data set comes first with a $sign before the variable name is. So age 85 is a new column inside the example1 data set. It is being made out of the old variable called age inside example1 minus 85. Likewise, grip strength is being made out of the old column called grip minus 9. Okay, with me so far? Okay. Then in terms of recoding, so I'm starting with two blank variables for my dementia groups. NF and NC are what they're going to be. NA means missing. Then I am systematically filling in zeros and ones. So for NF, if it's group 1, so note the equal here, then make it a 0. For NC, if it's equal to 1, make it a 0. For group 2, it goes 1, 0, and for group 3, it goes 0, 1. So now I have dem NF and dem NC that are my group comparisons, also known as contrasts, that will differentiate my three groups. Last but not least, filtering to cases that are complete on columns 1 through 6 of the data set, which are the variables of interest in the story. Okay, any questions on importing data or making predictors? Good so far? All right, moving along. Next step, descriptive statistics. Always making sure you know what you're looking at. As I told my previous class before, I've had many people give me data sets to analyze, and many of them have told me, oh, it's already been cleaned, it should be ready to go. Guess how many times it was actually ready to go with nothing crazy in it? Has never happened yet. Not yet, okay? And I've been doing analyses for other people for literally 25 years or so. It's never happened yet. So even if you know what you're going to do with respect to your models, do yourself a favor and run some descriptives and make sure that you don't have like, you know, minus 7,000 as a value somewhere where you're not supposed to. So I'm looking at descriptive statistics for my quantitative variables here. So I'm listing them out here. Cognition's going to be my outcome, age and grip, sex, which is coded men versus women, and my two new dementia contrasts. So I've got my mean cognition is 24, my mean age is about 84. I've got the min and max, most importantly, so our adults range from 80 to 97. Grip strength ranges from 0 to 19, and my outcome ranges from 0 to 44. Then we have frequencies for each category with respect to gender and dementia group. And these are important to note on the outset because of comparisons. So as you can tell, most of the people are in category 1, meaning they never got dementia. Right off the bat, how does that relate to power for group differences? What do you think the power is going to be for detecting like group 1 versus 2 rather than like 2 versus 3? Which one is going to have more power?
1 versus 2.
Yeah, the one where there's more people. So this is important for trying to make inferences about group differences. You can have a larger group difference that is nonetheless not significant relative to a smaller group difference if there's more people in the groups. It's all about the precision with which it's being estimated, which is a function of sample size. Yeah, group 2 and 3 is going to have less power. 3 is the people who started the study already with dementia. All right, and in R, I am using the describe function within the psych package, another exception to just base R, because it allows us to look at multiple variables and multiple statistics at the same time. So within dataset example 1, I am asking for those 4 columns. Then I'm using the table function to get descriptives by gender and group, including any missing values. That's what the if any does. And so this is the same information pulled out of R. Okay, ready to see a model? Why not? So main effects only model, meaning that there are no interaction terms yet. So I am going to throw in all of the predictors that are of interest right here for this demonstration. I'm predicting cognition with a fixed intercept, a slope of age centered at 85, a slope for grip strength centered at 9. And then these 3 variables are all binary, zeros and ones, where the first letter represents who the 0 is, and the second letter to me represents who the 1 is. These are my conventions. I'd want to introduce them to you. So how many slopes do I have in my model? Five. Yeah, here's an easy catch. Count up to the highest beta. That's your answer. How many fixed effects do I have in my model and don't say 5? 6. What's the 6th one? The intercept. So beta 0 is going to apply to everybody's score equally because it's not multiplied by anything. It's the fixed intercept. Then that prediction is going to be bumped up or down based on people's values for these other things. So the way that I've coded dementia then is going to directly give me which group. Who is N? N is none, by the way. Because they are the 0 in both places, the intercept is going to be for none. That means that none versus future, this is going to give me how different the future group is from none. This one's going to give me how different the current group is from none. What if I want to know future versus current? Can I do that? Yeah. I got to ask for this. I got to ask it to compute the slope that's going to be beta 5 minus beta 4. That's how I get the missing group difference. I have to ask for this separately. Yes?
I have a different question.
Yeah.
On betas 1 and 2 for age and grip, I know you're trying to center those variables, so why do you subtract the average of 85 and 9?
Because age is running from, let me see what the values were again, 80 to 96. And so I picked 85 because it was near the mean, 84.9 in this case. So what's going to happen is that this new variable is going to be 0 when it's for an 85-year-old. So like plus 5 would be 90, minus 5 would be 80. That way, my intercept is going to be within the scale of the possible predictors. It's going to be for an 85-year-old. Had I left this off and just stuck in age, everything would still run. But then who is my intercept for if I don't center? Say it louder. Now, if I don't center, if I forget this step and I just stick in age without making the new version, 0. What does age 0 mean? Like, just got born, right? Now, that's not wrong, but it's awfully weird to talk about an expected value for a newborn using octogenarian data. It's not wrong, but it's weird. Same thing here. Grip strength I centered near the mean, but if I forgot to center it, then beta 0 would be for somebody who can't even squeeze the thing, which hopefully there's nobody like that in the sample, but actually there is given the way that I simulated it. So the centering is designed to create a meaningful intercept. That's what this purpose is in this model. Okay. So now how do I tell my program of choice that estimate this model for me? Okay, well the E out here is what I'm saying is I'd like a linear regression, please. Okay, the package for that in Stata is regress. The package for that in R is LM, so that's coming on the next page. So you've probably seen those things before. Yep, here we go, lost it. So in Stata first, the outcome is first. Then comes the predictors, where C dot means treated as a quantitative variable. You don't always need that, but sometimes I get error messages in doing linear combinations without it, so I'm just in the habit of including it. Level 95 means, can I have a 95% confidence interval too? Sure you can. Commas in Stata, by the way, separate out commands from options for the commands. So then the output that I get from just this one line is this much right here. So we have the sums of squares table, which is not directly provided in R, but is provided in every other package that I've ever used, including SPSS. This summarizes the amount of information captured by the model versus the amount of information captured that's left over. That's sums of squares. So that's like the numerator of variance, essentially, without the denominator part. It's like, I got 18,385. Good for you. How many slopes did it take to get that? 5. Okay, here's your per slope information. How much information is left over? 47,000. Great. How many more slopes could you have added? 544. Number of slopes I spent plus number of slopes I could have added as denominator degrees of freedom gets me to 549. There's 550 people in this sample. The -1 is because I always have an intercept. The intercept stays no matter what else is in the model. This number right here has a special meaning, mean square residual or mean square error. Do you know what that is by another name? I'll give you a hint. Has to do with that thing right there. Close. Goes into R square. It's not F, but it's an ingredient of F. It's the denominator of F. This is residual variance. This number right here is the variance across people of these E's. Leftover variance. So it's the amount of cognition that is not predicted by age, grip strength, gender, and dementia. Now, is that a lot? I don't know. We got to put it into relative terms here. So F for the model, this is a test statistic that tells us the joint contribution of all 5 slopes together. F is per slope. So this number right here, information not captured divided by information left over. Each of these is a per slope unit That ratio is the 41. That's where that comes from. Prob greater than F, that's another name for p-value. So the p-value is 0 to 4 decimal places, meaning it is super duper unlikely that all 5 slopes are 0 in the population. Now we need this one, r squared. What's that mean? I can explain it like 3 or 4 different ways, but there's 2 that I prefer. What's an r square tell us? Say it louder. Yes. Yeah, so it's the proportion of variability in cognition explained by our model predictors. So I would say the proportion is 0.27 or the percentage is 27%. You can phrase it either way. This is an effect size for how well the predictors work together to predict cognition. This is the test of that effect size. So it's a joint hypothesis test for whether this r square is greater than 0. Yeah, the other definition of r square from the Zoomers is thinking about this in terms of r. You know what r is, right? It's a correlation. How do I talk about this with the word correlation in the sentence? It's a correlation between actual cognition and the cognition that is predicted from a linear combination of these things. The predicted cognition we call y hat. So any software package, including these ones, you can ask for it to create a new column in your data set that is y hat from your model. If you did that, you created what is the predicted cognition for this person, this person, this person, this person based on their predictors. You take that column of y hat prediction, correlate it with your actual y, that's r. And then do you know how you get from r to r squared? Yeah, exactly. Even at 3 o'clock on a Thursday, we got this. Yes, you square it. So yeah, this is the squared correlation between the y predicted by the fixed effects and the actual one. The latter idea generalizes to more complex models as well, like multi-level models and longitudinal models. So that's an important sort of core concept to keep with you. Adjusted r square is if I just take the residual variance from the empty model and then subtract this one and divide by the empty model residual variance, that's what I would get for this. So this is like change in the residual variance specifically is how this is computed, whereas this one is computed using sums of squares. And this is the square root of this, excuse me. Okay. So we have a significant model, so to speak. That's a global statement, meaning we have some significant prediction. Okay, what is the role of each variable in that prediction? Well, we come down here to our fixed effects table. This column, Stata labels as coefficient. You may also know that as estimate, as in point estimate, meaning this is the most likely slope given these data in this sample. Standard error is the next column over. How inconsistent is that slope expected to be across samples? So this number, for instance, for the age 85 slope, this is how far off on average the age slope is expected to be in any one sample from the population. The expected inconsistency across repeated samples. So if I start with this number right here, the age slope is minus 0.4. What's that tell me? Yeah, if age goes up, outcome goes down. That's what the negative sign means. Then we got to stick units into the story. So this is age in years. So for every additional year of age, that's my unit, cognition, my outcome, goes down by 0.4. So it's a negative association. Older people do worse on the test. Not too surprising there. Is that a strong association or not? I don't know that yet. But if I take this coefficient, divide by its expected inconsistency, which strips off the units as part of the denominator of standard error, then I get this thing. That's our test statistic for the slope. That's my t. A t of -3 has a probability value of 0.001. So there's like a 1 in 1,000 chance of observing a slope this big if the slope in the population is 0. And here's the confidence interval for the slope if you're so inclined. And beta 1, this is me being nice to you. So I'm labeling the output with respect to where it is in the equation. It would not do that for you in practice. Otherwise, I would not have a job if the output were actually understandable on its own. We call that job security, where I come from. All right, grip strength. How do we talk about that one? As for every unit grip strength, so this is for every pound you can squeeze, cognition goes up or down? Up by 0.6, significantly. So I would label each of these slopes using one of 4 phrases: significantly positive, non-significantly positive, significantly negative, or non-significantly negative. That combines the information about the direction of the association with our statement about how likely it is given the null hypothesis. Nothing on here directly tells me effect size, though. You would have to go to an extra step to convert these into effect sizes, which I did not do yet because I'm trying to focus on just the linear model aspect. Let's go down here to this thing called _CONS. What do you think that thing is? And I'll give you a hint by showing you how I labeled it over here. Beta 0. What's that? Intercept. Stata calls this the constant because that's from like 8th grade algebra language where like y equals mx plus b and b is the constant of the equation. I hate that term because guess what? These are all constants. So this is the intercept. And I also hate that it puts it last. But, you know, the people who made Stata did not ask my opinion before they formatted the output. So my fixed intercept here, beta 0, is 29. That's my expected cognitive outcome for what kind of person? 85, squeezes 9 pounds. Dude or chick? Dude. Yep, man instead of women. And somebody who is not going to have dementia. So I got to know who this is the intercept for so that I can think about what these binary slopes mean, right? So if my sex slope is negative, who's higher, men or women? Tricky. Who's higher? 50-50 shot. The slope goes to the 1 group. I'll give you a hint there. And men are higher. Yeah. So this is for men. If I turn this on, right, for women, you can think of the dummy code as like a switch that activates that slope. It brings the score down for women. So if you have a dummy coded predictor that's a negative slope goes with it, the 1 group is lower. Women are lower by 3.7 on this test. Likewise, relative to the none group as the intercept, the future and current groups are both lower by 5 points and 16 points, respectively. Yeah, dementia's bad for you, turns out. What do you think the difference is going to be between future and current? If future's lower by about 5 and current's lower by about 16, how different are those two? Like 11-ish and some change? So I can do the math and figure out exactly what the difference is here. But I can't subtract the standard errors and figure out what the standard error of the difference is. It doesn't work that way. Now, there are formulas by which I can compute that stuff by hand, but I don't want to. So I have to ask for this and that. That's what the next little piece of output here does. In Stata, to start with here, it's lincom, which stands for linear combination. The way that these types of statements work is that when you list the variable in the statement, you are talking about the beta it is going to have in the solution. So when I say, hey, dem nf, Stata is like, yes, you mean the -5? I'm listening. Multiply that by -1. Okay, I can do that. Then add to it dem nc. You mean the -16? I can do that. And multiply that by 1. So that's a fancy way of saying, I'd like beta 5 minus beta 4, please. And the answer, there's my 11-ish. So yeah, that's the missing group difference between the three groups. It's implied by the model, but not given directly. But we can always ask for it as a linear combination. Yes, I can. The reason that I wrote it this way is because of the way that it has to be written in other programs. I'm trying to keep the code as parallel as possible. In R, which we're going to have to get to next time it looks like, let me give you a foreshadowing here. That same idea is going to be operationalized as a string of zeros, -1s, and 1s. And the -1 is going to be applied to beta 4, and the 1 is going to be applied to beta 5. So I wrote it that way to make it look the same, and it works the same way in SAS as well. Linear combinations. Okay. How are we doing? See, I didn't know how to do this until way too late. And it's super useful to know how to get stuff out of the model that the model should give you but isn't giving you directly. Last piece of this then, in terms of extra pieces of information, joint hypothesis tests. If I want to answer the question about whether dementia matters in predicting cognition, I've got that slope, I've got that slope, and they together create this slope. I need to find a way to like lump that together to give me a joint, say, omnibus test of group differences. When you have a dummy coding scheme where you've carved up the variable into these separate predictors, it doesn't know that you'd like to put them back together again unless you tell it. So that's where these test statements come in. These are ways to request custom f-tests that lump together multiple slopes for a joint hypothesis test. So in Stata, for instance, I have two. The second one here is the one that I'm just talking about, the idea that I want to lump together the slopes for dementia group to create a two-slope test for whether either, basically, there's any difference across the three groups. And that is done by putting in parentheses, each slope that you want to lump and setting it equal to 0. Basically, what you're saying is, hey, what would happen if I took those both out? Can you tell me what the change in the model would be? Yes, I can. If you took those two slopes out, given that you have 544 you haven't spent yet, the F for that is 67. If that seems kind of strange, think of it this way. Another way of saying the joint test for the model R² would be to write this out and ask for the significance of every model slope at the same time. Age, grip, gender, both dementia slopes. If I want to ask for a joint test of all of them at the same time, all 5 slopes, that's an F of 41. That is literally the same thing that it's doing right here. That is what it's doing for you. So only in the case where you're testing all the slopes at the same time does it do it for you. If you want to be able to lump slopes together for other reasons, you have to be able to ask for it. So this one you don't really need. This is for pedagogy. This is the new one that we don't have otherwise. Okay, how are we doing? Yeah. Last but not least, making pictures. If you're describing the results of an analysis in a presentation or a poster, thou shalt not give me a table of results. right? Do not do that to your audience. They can't read the numbers and it's too much information to process. Thou shalt make some kind of picture to describe your findings. Stata makes it easy because you can ask for a bunch of predicted outcomes and a picture in 2 lines of code. So the margins command is how you can generate Y hats for anybody, for any combination of predictors. So I am asking for a range of low, medium, and high for age and grip while setting gender and dementia equal to 0, meaning I am controlling for those variables by saying, okay, these are going to be for men without dementia, but I want to show the effects of age and grip strength. This you read as from, by, to. Start at -5 in increments of 5 up to 5. Now, why am I doing -5 for age? Yeah, the centering. So how old in reality is somebody with a centered value of -5? 80. So the centering scheme that you use for your model, you have to carry forward in all the predictions for it. So what I'm saying in English is, I like a predicted outcome for somebody who is 80, increments of 5, 85, and 90. I'd like a predicted outcome for somebody with a grip strength of, if it's centered at 9, this is 6, in increments of 3, 9, and 12. And then Stata anticipates that you would like to make a picture. You just tell it what you want your x-axis to be, and it's like, here you go. So I have the effect of grip strength for people who are age 80, 85, and 90. These lines are parallel. Is that a coincidence or is that a consequence of my model? Coincidence or consequence? Consequence. Why are these lines parallel? There's no interaction. Another way of saying this is that the effect of age holds for everybody. The effect of grip holds for everybody. What if it's the case that how strong you are matters more in the really old than in the young old? Could that be? Sure. Or how old you are matters less if you're strong. Could that be a thing? Sure. So that's where we're headed next, is interaction terms. But we're not getting there today. Don't worry, I can see the clock. However, we have to go over the corresponding R code briefly, but I am realizing that there are questions about interaction terms in your formative assessment that we haven't covered yet. So you can either, formative assessment due on Monday, you can either look ahead in the slides and try to answer the questions yourself, or you can write down, yeah, I haven't learned this yet, and then we'll go over it in class. Either one is fine, because I haven't covered it. But if you have tried to do models with interaction terms, either in your research or in your classes, give it a shot. It's 2 questions about a model with an interaction term. Okay. Very briefly, the R code here to start off with so that I don't leave the R folks hanging. The LM call. Have you seen this before, R users? Okay, this is familiar? All right, I label all of my arguments, by the way. So this might be more code than you need to type, but to me the transparency is more important. So I'm using data set example 1. My outcome inside formula is cognition with a squiggle, meaning this is what my predictors are to be. And I have a 1 here. Why do you think I have a 1? What's that stand for? That's my intercept. Now, do I need to write the 1? I do not. It will run just fine and put an intercept in for you by default. But the reason that I keep the 1 here is to remind myself that in terms of the order of the fixed effects, 1 comes first. So I'm asking for a summary of the model. I'm also making a call to another function called ANOVA solely to get the residual variance, because it is not printed anywhere on the damn output otherwise, which frustrates me. So at the very end of the ANOVA output is the 88 residual variance that I was looking for. The rest of this output we will ignore because it's type 1 sums of squares. So the same information is provided in the R output, albeit in a different form. The sums of squares for the model, F-test, and R-square are sort of packed into this paragraph. They don't show you how it comes out, but the information is the same. It lists the intercept first, which I'm happy with, and all of the slopes, standard errors, and whatnot are exactly the same as this data output. All right. The new part, which I'm assuming you haven't seen, is the use of GLHT to get custom hypothesis tests. Have you done that before? Okay, that'll be a new thing for next time then. We'll work on that for next time. All right, 3:14 by my watch. Any questions before we call it not just a day, but a week? Yes.
It's an R question. I'm just getting an error telling me that my path doesn't exist.
Your path doesn't exist. All right. My guess would be that you have the wrong direction of some of your slashes, but I can help you troubleshoot that after class if you'd like. Sure. And yeah, I hang out after class usually in this room for a while. If anyone wants to stick around and ask questions, that's fine too. Quick question?
The residual variance is the same as the residual error, the E,
Mean square error or mean square residual, that's what this number is.
mean square, so it's the variance of E.
Yes. Yes, variance of E, that's what this thing is. And it's nowhere else in the output, excuse me, but they give me the square root of it. Nah! So, yeah. Anyway. All right, thanks for being here, folks. I will hope to see you next week. Give your formative assessment a shot, and we'll talk about it on Tuesday. Bye, Zoomers. Thank you.